Welcome to The Explainer. Today, we're going to pull back the curtain on the incredible process that turns something as abstract as computer code into a physical microchip. You know, the brain inside pretty much every piece of tech we use.
I mean, really, how does that even work? How do you get from lines of text in a file to a real, tangible object that can run billions of calculations every single second? It honestly feels like magic. But it's not. It's actually a highly structured and, frankly, fascinating engineering journey, and we're going to walk through it together, step by step.
So this whole process, it has a name, the RTL to GDSI flow. And to really get our heads around it, we're going to use an analogy that I think works perfectly. Imagine we're building a microscopic city. We're starting with just the architect's dream, and we're going to end up with a detailed, ready-to-build city plan.
Okay, so before we dive deep into the weeds, let's pull up the map for this journey. If we get the big picture first, each stop along the way is going to make a whole lot more sense.
We're going to break this down into 5 key phases. We'll start with that high-level vision, then see how the code gets turned into actual building blocks. After that, we'll plan the layout of our microscopic city, connect everything with wires, and finally, do the last inspection on the blueprint before we send it off.
And these are the real nitty-gritty steps inside those phases. As we go down this list, I want you to notice a pattern. Each step takes the design from something abstract and turns it into something more concrete, more physical. With every single stage, we're getting closer and closer to actual silicone.
All right, let's kick things off with our first major phase. This is the moment where the soul of the chip, the code that describes what it's supposed to do, actually starts to take on a physical form.
This very first step is called logic synthesis, and its entire job is translation. Basically, a super smart piece of software reads all that human-written code and converts it into what's called a netlist. Now, you can think of the netlist as the official parts list for our city, a detailed inventory of every single component we need, things like AND gates and flip-flops, which are the fundamental Legos of digital logic. This is the moment our idea becomes a real bill of materials.
Now, to get this job done, the synthesis tool needs 3 things. First, obviously, the code itself, the design. Second, it needs a standard cell library. This is just a big catalog of all the pre-designed parts, our prefabricated buildings, that it's allowed to choose from. And third, it needs a constraints file, which lays down the law. Things like, this chip absolutely must run at this clock speed.
And boom! What you get out the other side is no longer just abstract code. You get a gate-level netlist, which is this massive text file listing every single gate and exactly how it connects to every other gate. You also get reports that give you a first guess at how big and how fast your design is going to be.
You know, what's really cool here is that it doesn't matter if you're using the big guns from Synopsys and Cadence or powerful open-source tools like Yosis. The fundamental job is exactly the same. They all take in that abstract design, look at the library of available parts, follow the rules you gave them, and spit out a physical plan. Okay, so quick recap. We've got our complete shopping list of all the parts for our city. The next phase is all about urban planning. We have to figure out where every single one of these millions of components is actually going to go.
This happens in a 2-step dance. First up is floor planning. This is where we decide the chip's overall size and shape, we place the big landmarks like memory blocks, and we lay out the main power grid. Then comes placement, where a sophisticated algorithm finds the best possible spot for every single logic gate. We're talking millions of them.
So what does the tool need to pull this off? Well, it needs our netlist, of course. That's the list of all our buildings. But it also needs a new kind of file, a left file, which describes the exact physical shape and size of each one of those buildings. And finally, it needs the city's zoning laws, the rules for the overall layout, like its dimensions and how densely we're allowed to pack everything. And that brings us to a really key number in chip design, 70%. A super common industry target for something called core utilization is right around there. Now you might be asking, why not 100%? Why not use all the space? Well, it's because the planners have to intentionally leave that other 30% empty. And that space isn't wasted, not at all. It's absolutely crucial for the next step, because that's where all the roads and wiring are going to go. So the really big deal coming out of this stage is a file called a DEF. This is our master city plan. And for the very first time, every single one of those millions of components has a precise X and Y coordinate. We also get these really cool congestion maps. Think of them like a traffic forecast, showing us exactly where we might run into wiring traffic jams later on.
All right, so all of our city's buildings are in place. But there's a problem.
They're all just sitting there, isolated, with no power and no way to talk to each other. It's time to build the city's most critical infrastructure.
This means tackling two huge jobs. First is something called clock tree synthesis, or CTS. The best way to think about this is like building a master clock for our entire city to make sure that every single traffic light turns green at the exact same instant. It's all about synchronization. The second job is routing, which is literally laying down millions of tiny metal roads to connect every single building, just like the net list told us to.
So to lay all this groundwork, the router needs a few key things. It needs our city plan, the DEF file with everything in its place. It needs the specs for our master clock, how fast it needs to tick, and crucially, it needs the technology's building codes, super strict rules that say exactly how wide wires can be, how close they can get to each other, and which metal layers they're allowed to be on.
The output here is a fully wired-up layout, sure, but the really critical piece is a file called a SPEF. This file contains what's known as parasitic data, and it's essential because it models the real-world physics of all those tiny wires. It tells our analysis tools how they're going to act like tiny speed bumps or antennas affecting the signal. This data is absolutely vital for our final inspection.
Okay, we're on the home stretch. Our microscopic city is designed, all the buildings are placed, and every road and power line is wired up. But before we can hit print and send this blueprint to the factory, it has to pass a bunch of really, really tough final inspections.
This stage is called sign-off verification. And here's the most important thing to get. These checks don't change a single thing about the design. Their only job is to give it a final thumbs up or thumbs down. They use incredibly accurate, specialized tools that act as the ultimate quality control gate before we commit millions of dollars to manufacturing.
So what's on this final inspection checklist? Well, there are 3 absolute must-pass tests. First, static timing analysis, or STA, which confirms the chip is actually fast enough. Second, design rule check, or DRC, which meticulously checks the layout against thousands of manufacturing rules. And third, layout versus schematic, or LVS, which makes sure the final drawing is electrically the exact same as our original blueprint.
So let me put it this way. LVS asks the question, did we build the right thing? It compares the final function to the original intent. Meanwhile, DRC asks a totally different question. Did we build the thing correctly? It just checks the physical geometry against the rules. Both of these have to be 100% clean, no exceptions.
And once every single one of those checks comes back clean, that's it. The entire design is exported into one final absolutely massive file, the GDS. This is the master blueprint that gets sent to the fabrication plant. It contains every single polygon on every single layer needed to build the chip. It is the culmination of this entire journey, the process that ensures that tiny, microscopic city in your pocket works perfectly every single time.